Now you are able to see the screen, or is the slide visible for you?
Yes, sir.
Okay, I think procedure is correct. These are all the things that we learned. Previous class we had taken these equations, no, modified Goodman and Baskin's equation. This we have noted down, no, previous class. Yeah.
Yes, sir.
And had we solved this problem? Yeah, we had solved this problem also. Have we taken the second problem? Did we solve the second problem? Yeah. Please
Yes, sir.
check whether we have solved both problems or only one problem we have solved. How many we have solved? Yeah, can anybody tell me so that I can go to the next one, next topic? Yeah, Sandesh, how many we have solved? Can you hear me? Yes? Mithun, can you hear me?
We have solved both the problems.
We have solved both the problems, huh?
Yes, sir.
Okay, then we'll go ahead with the next part of the topic. That is constant life diagrams. Please note down constant life diagrams. Hello?
Yes, sir.
Can you hear or you cannot hear, man?
We can hear, sir.
You can hear. Are you able to see the screen? Please check. Tell me whether the screen is visible.
Yes, sir.
Is the constant life diagram screen is visible or not?
Yes, sir.
Okay. Now note down the heading as constant life diagrams and note down the sketch. Note down the sketch here. This is compression, that is minus SY, yield stress, that is compression. This is compressive mean stress. Plus SM stands for the tensile mean stress. Then this is a tensile yield stress, and this is SU here. That is ultimate stress. Okay. This is SF. Okay, fatigue limit or endurance limit. These intercepts, okay, these intercepts are SNF, that is fatigue strength for fixed number of cycles. Normally it will be 10 power 6. And this point is S dash Y. This is 10 power 3 number of cycles, 10 power 4 number of cycles. This curve is for 10 power 5. And this is for 10 power 6 to 10 power 8. Okay. And this is stress amplitude. And this is positive mean stress. And this is negative mean stress. Have you noted down the sketch, or are you noting down?
Noting down.
Yeah. One of you please answer. Whenever I ask something, please answer so that I'll have clarity and confirmation that it is visible.
Yes, sir.
Yeah. Okay, I'll start explaining this. Okay, so basically, right. So these are all the straight lines for modified Goodman, okay, and Morrow equations, and then this is essentially done for fully reversed. That is alternative tension and compression. The shaft subjected to alternative tension and compression for every 180-degree rotation. So that's why we call it as R is equal to -1. This we have learned in our previous discussions. Okay, so this is the positive mean stress, this is negative mean stress. So the intercepts SNF, okay, this is SM is equal to 0. So these are all intercepts SNF. So the intercepts SNF for a given life are found from the fully reversed, that's what I said, alternative tension and compression modeled SN curves. So the modified Goodman straight lines are passing through these intercepts, okay, and the ultimate tensile strength. So from ultimate tensile strength, the modified Goodman lines pass through these intercepts. So these intercepts indicate this curve is for 10 power 6 number of cycles and so on. Next. So that's about the constant life diagrams. So this diagram indicate the constant life of the components. Now let us look at strain life approach. This is a second part of your module 2. So far what we have learned is the stress life approach. So it was SN curve. That's what we have learned. Correct? Okay.
Yes, sir.
S stands for stress, number of cycles. But here it is strain life approach is the next thing that we need to learn. So before we go to the strain life approach, so as I said previously, so far what we have learned is stress strain diagram. So that is stress versus number of cycles. So SN curve is what we learned. So now it is going to be strain versus number of cycles approach. So for that to be understood clearly, we need to look at monotonic tension test, stress strain behavior. Anyway, this again is the stress strain diagram that we have learned in our MT lab during tension test. So what we did is we took a specimen, marked the gauge points, and then we mounted the specimen on universal testing machine UTM. Correct? Then and the tension these whatever the tensile stress that or yield stress that we find out from the tension test using UTM, its relation to fatigue behavior is remote. Okay, so that's what here we are doing. So monotonic behavior is obtained from a tension test in which a specimen with circular or rectangular cross section with uniform gauge length is subjected to monotonically increasing tensile force until it fractures. This is the essence of entire stress, tension test that we do in our UTM in our material testing lab. Correct? So what we do is we take a specimen, mark the gauge points, mount it on two supports in a universal testing machine, and subject that for uniform we subject it for elongation, and for every load we calculate using extensometer. We are going to find out the change in length. Correct? Then using the load, and we know the original area of cross section of the specimen, using that we get stress that is given by load by area of cross section. Using extensometer, we find out change in length. Then what we do, we find out strain using change in length by original length, delta L by L. Correct? So we get stress and strain, and then we are going to plot stress versus strain, and we are going to get stress strain curve. Correct? Do you agree with me?
Yes, sir.
Okay. So now from monotonic is nothing but in a single direction. That's all. Single direction monotonically. Okay. So in monotonical uniaxial stress, so in UTM we know in only one direction. Correct? So the uniaxial stress and behavior can have engineering. What is the difference between engineering stress strain and true stress strain relation is that in nominal stress we will have stress is equal to load by original area of cross section AO. Okay, this is where we get the nominal stress. And then in actual condition, what will happen, as you keep loading the component, its diameter keep decreasing and decreasing, correct? And thereby necking formation takes place. Do you agree?
Yes, sir.
Yeah. So as you keep loading the component, okay, then what will happen? The original area will not be there. It starts losing its diameter, and then the true stress is obtained when you are going to take the instantaneous area of cross section, and P, load versus instant area of cross section, will give you true stress. That is the actual stress at that point. Okay, so that is the difference between the nominal stress and true stress. Similarly, the engineering strain and true strain, that's the difference. So in engineering strain, we take change in length by original length. But what will happen in actual condition of testing, the component or specimen keeps elongating continuously because of application of load. So therefore, you will have true strain is equal to change in length by instantaneous gauge length Li. So that is called true strain. So the difference between true stress and engineering stress and strain, true stress and the true strain, we have understood. No, true stress and true strains are at instantaneous area of cross section and instantaneous length, correct? Okay, that is what true stress and true strain is all about. Whereas engineering stress and strain are at original area of cross section of the specimen and original length of the specimen. Okay, that is the difference between engineering stress strain and true stress strain. Got my point?
Yes, sir.
Okay. Now, so for small strains, we can take engineering stress to be equal to true stress. Okay, for that is say P by A naught, we can take it as P by AI, that is instantaneous area of cross section. Engineering strain, that is delta L by L naught, to be equal to delta L by what? True strain. Delta L by what now? True strain is delta L by
Li.
Li, that is instantaneous gauge length. Okay, that is true strain, and engineering strain is change in length by original length L naught. So, however, for larger strains, that is for plastic deformation, for plastic deformations, the difference becomes appreciable. That is, you cannot equate engineering stress to true stress, and you cannot equate engineering strain to true strain. They will be totally different for during plastic deformation stage. So you have two zones. One is elastic region, the another is plastic region in case of stress strain diagram, correct? So in elastic region, the component will come back to its original shape and size upon the release of load, but whereas in plastic deformation, it cannot regain its original shape and size. Okay. So for plastic deformation, a constant volume condition can be assumed up to necking. So can you see this picture clearly? Is this picture visible for you?
Yes, sir.
Yeah. So the picture A that is shown here is A naught, that is original gauge section. Second one is uniformly elongated gauge section, and third one is gauge section at fracture. This is the necking that is taking place. That is, there is a formation of a neck region before it fractures. Okay, so this is how engineering stress strain will be, and this is the curve where we get true stress strain, because the elongation will be enormous in the plastic region. That is what we have described out here. So referring to figure, we have original gauge length or gauge section, uniformly elongated gauge section. This is true for small strains. But as in the plastic deformation or enormous strains, there is going to be formation of necking. There is going to be decrease in area of cross section and increasing in instantaneous gauge length. Okay, this condition will happen before it fractures. This is how the fracture takes place and in the specimen during our tension test. Okay. Next, so the indicators of energy absorption capacity of the material are resilience and tensile toughness. So what is the resilience? So coming back to this, as you keep loading the component, okay, the energy is absorbed by the specimen. Okay, energy is absorbed by the specimen as you keep loading the specimen. So that energy absorbed by the material of the specimen is called the resilience. Okay, that is the elastic energy absorbed by the specimen, then that is equal to area under the stress strain curve within elastic limits. That is, draw the stress strain curve within elastic limit, take slope. Okay, take slope, you are going to get a triangle. From that triangle, area of triangle is given by what? Half base into what?
Height.
Half base into height, correct. So that is the area which will give you the energy absorbed U, that is given by, so you are plotting load versus deformation. So load in the y direction and deformation in the x direction. So when you take slope, it's going to be a triangle. So area of this triangle will give you the energy absorbed by the material of the specimen. So therefore it is half F into Y, that is half base into height. So this is the energy absorbed by the material of the member during tension test. Then what is tensile toughness? It is the energy per unit volume absorbed during deformation up to fracture and is equal to total area under the engineering stress strain curve. Okay, where is engineering stress strain curve? This is the engineering stress strain curve. The total area that we are going to have in engineering stress strain curve will give us the tensile toughness. Are you there? Could you understand?
Yes, sir.
Now, if you take only the triangle over here within elastic limit, okay? So in y direction it is F, in x direction it is Y. So half base into height of this triangle will give you the resilience, whereas the total area under the engineering stress strain curve will give you what? Will give you what?
Toughness.
Yeah, exactly. That is, you are going to get the tensile toughness is given by energy per unit volume absorbed during deformation and is equal to total area under the engineering stress strain curve. Now, the total strain is composed of two components. What are they? One is the elastic strain and another is plastic component. So we have two regions in a stress strain curve, as I said, as we discussed previously. It will contain elastic region and another one is what region? Another one is
Plastic.
plastic region. Okay, so the strain consists of two parts. One is the elastic strain, wherein the original regains its original shape and size upon release of load, and the plastic component where it cannot come back to its original shape and size. Our elastic strain is given by stress by Young's modulus. From which expression we get this? Strain is equal to stress by Young's modulus. This is from
Hooke's law.
exactly, that is stress is proportional to strain under within elastic limits. So removing proportionality constant, we get Young's modulus. Correct? Huh? So strain is equal to stress by Young's modulus. And plastic component we have C is equal to, this is the strength coefficient, this is the plastic component, and this is the stress, and K is the strength coefficient, and the small n that we have here is the strain hardening component. So the total strain will be given by the elastic strain component and plastic strain component. Elastic strain is sigma by Young's modulus plus this is sigma by k to whole to the power 1 by n. So what this n gives us is it gives a measure of materials work hardening behavior and is usually between 0 to zero point 0.5, and k is the strength coefficient. Okay, it's a coefficient of strength. Okay, that is to be multiplied. Okay, to get, so this should have been epsilon p anyway. So that you please correct it over there. So now what you do, take out your notebook, okay, and note down the elastic strain is equal to sigma by Young's modulus, and the plastic component is given by, you directly come over here, sigma by k whole to the power 1 by n. Note down this equation in your notebook. Note down both the equations. Where k is strength component, okay? K is strength component and n is strain hardening exponent. N is a strain hardening exponent, k is strength coefficient. K is a strength coefficient, n is strain hardening exponent. N is strain hardening exponent, whereas k is strength coefficient. Please note down this equation. Note it down.
Yes, sir.
We'll move to the next topic. So what we learned so far, I'll just sum it up. So we learned about constant life diagrams. So these are the diagrams which are based on Goodman's and Morrow criterion. Okay, and SNF gives you the intercepts. So you have positive mean stress and negative compressive mean stress over here, and these curves will give you, okay, finite fatigue life. Okay, and next what we learned is the strain life approach. This is a new approach. So to understand strain life approach, what we learned is the regular stress strain diagram, how we plot. So from there, we learned about engineering stress strain and true stress strain. So when we use original area of cross section, that will give us engineering stress. Okay. If we use instant area of cross section, we get true stress. So instant area of cross section, as we saw in this diagram, when the necking happens, there's going to be decrease in diameter, correct? So decrease in diameter, what will happen to the stress? Stress will go up. So the true stress is always greater than the nominal stress, because in nominal stress, we'll use original area of cross section, whereas in true stress, it is going to be instantaneous area of cross section, which is always less because of necking before fracture. And engineering strain is delta change in length by original length, whereas true strain is change in length by instantaneous length. Okay, and then we learnt about the strain components. The total strain is composed of
Elastic and plastic strain.
yeah, elastic and plastic strain given by sigma by E plus sigma by K whole to the power 1 by N. K is strength coefficient, whereas N is strain hardening exponent. Correct? Now, we'll move to the next one. Yeah, strain controlled test methods. How strain control test method are carried out? So an important aspect of fatigue process is plastic deformation, because fatigue leads to failure, crack nucleation, crack propagation, and final fracture. Okay, so that is what the fatigue process is. So fatigue process is a plastic deformation because it leads to fracture finally. So fatigue cracks nucleate from plastic straining in localized region. Therefore, cyclic strain control test can be better characterize the fatigue behavior of a material than cyclic stress controlled tests can. Can you understand what this is? What the meaning of the sentence is that the strain controlled tests will give us better understanding of fatigue behavior of material than because of SN curve, that is stress controlled fatigue test. Is that okay? That means inference is that the strain controlled tests will give us better fatigue behavior understanding of a material than stress controlled tests. Could you understand it now?
Yes, sir.
Because strain will have the instantaneous area of cross section, instantaneous gauge length, and so on. So the strain will give us clear picture of fatigue because fatigue process involves crack nucleation, crack propagation, and fracture. So here also it's going to fracture finally after necking. So therefore he says the strain control test will be better than stress controlled test. Now, how the strain control testing is conducted? So it is essentially conducted on a servo-controlled closed-loop testing machine. If you remember, in fatigue testing machines, the last one was closed-loop control, the fatigue testing machine. So the same can be used for the strain-controlled testing also. An unnotched specimen with a uniform gauge section is as shown in figure and is subjected to axial straining. So this is the sketch of a specimen. An extensometer is attached to the uniform gauge length. So again, it's same as what we do in our universal testing machine. We attach an extensometer. What is the function of extensometer? Dhanush?
Sir, to see the deformation, sir.
Excellent. Okay, excellent. So that is to obtain the to take the note of change in length. The extensometer is attached and measure strain over gauge section. So this is the specimen. An extensometer is used to note down the strain over the gauge section. Right. So this is how the specimen will be. And then a standard strain controlled test consists of constant amplitude, completely reversed straining at a constant strain rate. So constant amplitude in the sense we apply plus 50, minus 50 or plus 100, minus 100. There is no variation in amplitude and completely reversed straining, that is plus 50, minus 50 like that at a constant rate, that is so many cycles per minute. That's it. So commonly used strain signals are the triangular or sawtooth or sinusoidal waveform. Sinusoidal waveform is alternatively positive and negative of constant amplitude. Okay. Stress and plastic strain are recorded periodically throughout the test and cycling is continued until fatigue failure occurs. This is how a strain controlled testing is carried out. So what is it exactly? Going by the inferences, strain controlled tests can give us better understanding of fatigue behavior of material than stress controlled test. So a specimen, unnotched specimen, please remember this. Please note this, unnotched specimen, there is no presence of notch. So it will be subjected to axial straining and an extensometer is used to note down or measure strain over the gauge length. Okay. And then the strain control test is conducted with constant amplitude, completely reverse straining, and at a constant strain rate. And normally sinusoidal or sawtooth waveforms are used as signals. And stress and plastic strains are recorded periodically till the failure, which will give us the final fatigue failure readings. Could you understand how strain controlled testing is carried out? Okay. Are you there?
Yes, sir.
Yes, sir.
Fine. Next. Now, use this strain-based approach to life estimation. So what we learned is strain life approach we learned. How strain controlled testing is carried out. That we learned just now. Now let us look at how the life estimation can be made of a component, okay, based on strain based approach. Okay, so this is the heading. Please note down this heading: strain based approach to life estimation. Note down the heading. Strain based approach to life estimation. Yeah. Okay. So why we adopt a strain-based approach is strain can be measured. That means it will give us the quantitative measure rather than the stress. Stress you cannot get quantitatively. So strain can give you quantitative measurement of the strain, and strain is a good quantity for correlating with low cycle fatigue. So low cycle fatigue is where the component will fail before 1000 cycles. That is the low cycle fatigue. So strain is a quantity, good quantity for correlating with low cycle fatigue. Example, somebody's noise is coming. Please avoid the noise there. Okay. Now, example, gas turbines operate at fairly steady stresses, but when they are started and stopped, they are subjected to very high stress range. So stresses are more difficult to measure or estimate than strains because you cannot have the instrument to measure stress directly, but whereas you can have instruments to measure strains directly. So in a notched component, so notch is a discontinuity. Please remember, in a notched component or specimen, when it is subjected to cyclic external loads, the behavior of materials at the root of the notch is best considered in terms of strain. Okay, so please remember, and the at the zone of notch, root of notch, okay, notch or presence of a hole or a notch or a groove. So root of the notch is best considered in terms of strain. That is, it is better to note down the strain at the root of the notch. Now, strain leaf based design method can be used for relating fatigue life of notched parts to the life of small unnotched specimens that are cycled to the same strains as the material at the notch root. That is, final inference is fatigue damage is damage is assessed directly in terms of local strain. Okay, that is near the root of the notch we are going to measure the strain, and then fatigue damage is assessed directly in terms of local strain, because at the root of the notch there is going to be the presence of local strain, so we can directly assess fatigue damage at local strain. So therefore this approach is called local strain approach. Are you there? Could you get it now? So only
Yes,
thing
sir.
is,
Yes, sir.
at the root of the notch, we are going to measure the strain. So that will give us fatigue damage directly in terms of local strain, that is strain at the notch. Okay, and this approach is called local strain approach. So note down this last sentence, which is in italics. Please note down this sentence. In case of strain-based approach to life estimation, fatigue damage is assessed directly in terms of local strain. So local strain, that is at the root of the notch. That's it. Local strain. And this approach is called local strain approach. Okay, we'll go to the next slide.
Yes, sir.
Okay, yeah. A reasonable expected fatigue life based on the nucleation or formation of small macro cracks can then be determined if one knows local strain time history at a notch in a component and the unnotched strain life fatigue properties of the material, right? That is, we can estimate reasonably the expected fatigue life based on unnotched specimens strain life fatigue property and also local strain time history at a notch in a component. So therefore, the strain life curves are often called as low cycle fatigue data because much of the data are for fewer than 10 power 5 number of cycles. Okay. So strain life curves, unlike in stress life curves, strain life curves are normally called as low cycle fatigue data. That is the failure that has happened before 10 power 4 or 10 power 5 number of cycles. Okay, please note down this last sentence. The strain life curves are often called as low cycle fatigue data. Please note down this sentence which is written in italics. Okay, finished. Shall we go to the next slide?
Yes, sir.
Yeah. Now, the strain life fatigue curves plotted on log law scale or as. So this is the fatigue life. One is the elastic strain, another is plastic strain. So what is elastic strain? Can someone tell me? What do you understand by elastic strain? Simple.
Which can regain its original position.
Yeah, that is with a strain within elastic limits is elastic strain. That's all. Fine. Now, then what is plastic strain?
Deformation occurs.
Deformation occurs in both cases. Then what is the difference between elastic and plastic strains?
Permanent deformation occurs.
Yeah, permanent deformation occurs in plastic zone. Okay. So here, if you see, so 2NF is the number of cycles or reversals to failure is plotted on x-axis, 2NF, and then this is the strain amplitude on a log scale that is plotted. The curve that is indicated here, okay, this is the elastic strain, okay, and the steeper reduction, this line is called plastic strain. This line indicates plastic strain and this line indicates elastic strain. So at large strains, plastic strain component is predominant. At small strains are longer life. So if you look at elastic strain curve, it will have longer life. That is because NF is plotted on x-axis. This curve indicates longer life which will happen in elastic strain condition. Whereas in plastic strain condition, the life of the component drastically gets reduced. So therefore, at large strains, plastic strain is predominant as compared to elastic strain, or for longer life or small strains, elastic strain component is predominant. You are there now. So elastic strain is for longer lives, whereas in larger strains, plastic strain component is going to be very important or is predominant. Is that okay? Next. Yeah. For lives less than 2NF, the deformation is mainly plastic. That means the failure takes place at a very less number of cycles, less than 2NF. For lives greater than 2NF, deformation is mainly what? Elastic. Okay, because it withstands larger number of cycles. So this is the difference between plastic and elastic strains. So the transition fatigue life decreases with increasing hardness for steel. So what is transition fatigue life? The point where the elastic strain curve and plastic strain curve, they intersect at one point, and that point is called transition fatigue life. So the transition fatigue life decreases with increasing hardness of steels because they tend to break faster. The strain based approach unifies the treatment of low cycle and high cycle fatigue, and this approach also applies to long life applications where small plastic strains may exist. Is a comprehensive approach because we can directly measure the strain. Okay, so now what you do is please note down this. 1 second. Yeah, please note down this picture, this figure. Okay, this is strain amplitude in y direction on log scale. This is reversals to failure. Reversals to failure, that is 2NF again on log scale. This curve is elastic strain curve. This is a plastic strain curve. The intersection of elastic and plastic strain is called transition fatigue life, which will decrease with the hardened steels, and this curve will give you the total strain curve. Please note down this sketch. Are you noting down?
Yes, sir.
Okay. Okay, come back to the class now. Okay, the life at which elastic and plastic components of strains are equal is called transition fatigue life. This is the life at which curves will intersect as shown in figure. Okay, so therefore the equation for transition fatigue life is given by 2NF is equal to fatigue ductility coefficient epsilon dash F into Young's modulus divided by the fatigue strength coefficient sigma dash F whole to the power 1 minus B minus 1 by B minus C, that is fatigue strength exponent, and fatigue ductility exponent is C. Note down this expression. Equation for transition fatigue life is given by. Note down this equation and this description also. Are you noting down? So the life at which, so in terms of life, if you say the life at which elastic and plastic components of strain, elastic and plastic components of strain are equal is called transition fatigue life 2NF. Okay, are you there?
Yes, sir.
Okay, please note down what is transition fatigue life and what is the equation for transition fatigue life and description for each of these components. Epsilon dash F is fatigue ductility coefficient. Capital E stands for Young's modulus. Sigma dash F, fatigue strength coefficient. B is fatigue strength exponent. C is fatigue ductility exponent. Note down this equation. Write down the equation clearly. So the life at which, okay, that is 2NF life, at which elastic and plastic components of strain are equal is called transition fatigue life, okay, and it is the intersection of elastic and plastic strain curves. Is that okay? Finished, huh? Finished?
Yes, sir.
Okay. Anyway, we'll come back as to what we learned today in total. So basically, we started with monotonic tension test. So we learned about the engineering stress and strain and true stress and true strains. That's what we learned. Next, what we learned is for small strains, engineering stress is equal to true stress and engineering strain is equal to true strain. And then we learnt about what is engineering stress strain curve and how a true stress strain curve looks like, and what is necking is what we learnt. Okay, after that, what we learnt is the two things that are that can be observed from the stress strain diagram is one is resilience, another is tensile toughness. So resilience is the energy absorbed by the specimen, okay, which is given by the area under the triangle in the stress strain curve, that's given by half F into Y. And the tensile toughness is the energy per unit volume absorbed during deformation, and it is equal to total area of engineering stress strain curve. Okay, and then the total strain will have two components. One is elastic strain component, another is plastic component. That is given by the equation that we have noted down. And then strain controlled test, how the specimen is prepared. An extensometer is used to measure the strain over the gauge length, and then we are going to, and then the normally the test is conducted at constant amplitude and at a constant strain rate, and normal signals will be either triangular or sinusoidal waveform signals are used for conducting the test. And then what we learned is strain based approach. And we learned about how the strain based approach is more better than the stress based approach. Okay, and then we learned about the strain life fatigue curve, so which contains elastic strain and plastic strain. So strain within elastic limits is elastic strain, So uncontrolled deformation is plastic strain. And when you plot elastic strain, this is usually for larger number of cycles or longer life, whereas the plastic strain we are going to get for shorter lives. And there is a point where you will have elastic strain and plastic strain intersect. That point is called transition fatigue life, where the life 2NF life is same for both elastic strain and as well as plastic strain. So that point is called transition fatigue we learned, and then this is the equation for transition fatigue that we learned. Is that okay? So next we are going to learn about determination of strain life properties. Okay, one second. So who are all present? All are present, no? All are present. Mithun, Dani, okay.
Yes, sir.
And who else? Sandesh is present. Then Monambal, Sukrut, Sandesh. Okay, all six are there, no? Okay. So shall we meet again? We are meeting tomorrow at 8:30. Okay.
Okay,
Fine.
sir.
So tomorrow 8:30, I'll send the same as today. I'll send link at 8:25. You join at 8:30. We'll have the module 2 next part. Is that okay? Fine.
Yes, sir.
Okay, sir.
Right. Okay. Have a good day. Bye.
Bye.